All right, let's pull back the curtain on the universe for a second. We're going to dive into these hidden, tiny rules that secretly run everything around us. And you know what? It all kicks off with a really simple question you've probably asked yourself before.
I mean, seriously, think about it. This happens every single time, right? Without fail. It feels like a basic law of the universe. But why? What's actually going on? Well, the answer isn't some kind of magic. It's just statistics. And to really get our heads around that, we need to first figure out what it is we're even looking at.
So, when you feel that your coffee is hot, you're measuring its macrostate. That's the big picture view. You know, stuff like the temperature, the pressure, the volume. It's everything we can see and feel directly. But here's the catch. That big picture is actually made up of a truly mind-boggling number of tiny, hidden details underneath.
Okay, to make sense of this, let's just shrink the problem way, way down. Let's forget about the trillions and trillions of particles in a coffee cup for a minute. Instead, let's think about something way simpler. How about just flipping two coins?
Okay, now this is where it gets really cool. The macrostate is just the overall result, right? You either get two heads, two tails, or one of each. Simple enough. But look closer at that one of each macrostate. It can happen in two totally different ways. You could get heads first, then tails, or you could get tails first, then heads. Each of those specific combinations, that's what we call a microstate. So there you have it. A microstate is like the ultimate nitty-gritty, zoomed-in description of what's happening. It's not just the coffee is hot. It's the exact position and the exact speed of every single molecule in that coffee at one specific moment in time. The analogy is perfect. If the macrostate is the forest, the microstate is knowing where every single tree, branch, and leaf is.
And this chart really drives the point home. Look, any single specific flip, like getting heads then tails, is just as likely as getting heads then heads. One is not luckier than the other. But the overall outcome of getting one of each is twice as likely to happen. Why? Well, simply because there are two different ways, two microstates, that give you that same result.
And that right there is the key. The whole thing, the crucial point, is just about counting the ways something can happen. The universe doesn't secretly prefer one outcome. It's just stuff is more likely to happen if there are more ways for it to happen. Now, how in the world do physicists keep track of all these possibilities when we're talking about more than just two coins? Well, they have a pretty incredible map for that.
Right. So to actually visualize every single one of these possible microstates, physicists came up with a truly wild conceptual tool.
It's called phase space. Okay, so imagine a giant map. But instead of mapping out cities and roads, this map plots out every single possible state a system can be in. Every single point on this map is one unique microstate, a perfect, complete snapshot of where every particle is and how fast it's moving.
So to make this feel a little less abstract, check out this simple pendulum. In our world, on the left, it just swings back and forth. But on the right, in its phase space, which is just mapping its position against its velocity, its state traces this perfect circle. As time goes on, the system is just taking a walk along this path in its own little phase space.
Okay, but a pendulum is simple. What about a gas? Now it gets crazy. For every single particle, you need 3 numbers for its position, x, y, and z, and 3 for its momentum. That's 6 dimensions per particle. So the phase space has 6 n dimensions, where n is the number of particles. For something like a cup of coffee, we're talking about a space with a number of dimensions that is just, you can't even picture it. It's beyond imagination.
So we've got these two worlds, right? The macro world we can actually see and measure, and this hidden micro world with this insane number of possibilities. The big question is, how do you connect the two? Well, a guy named Ludwig Boltzmann came along and built the bridge.
This was the genius puzzle he solved. He figured out a way to take that almost infinite number of microstates and link it directly to a single measurable thing in the big picture world, a property you've definitely heard of: entropy. And this is it. S equals K log omega. It looks so simple, doesn't it? But this little formula is honestly one of the most important equations in all of physics. Its implications are just staggering. All right, let's break it down real quick. S is for entropy, which people often call disorder. K is just the number, Boltzmann's constant that makes the math work out. But the real star of the show here is omega, that big Greek letter. Omega is just the number of microstates. It's the count of all the different macroscopic arrangements that result in the same macro state. That's all entropy is.
It's just a way of counting how many different ways a particular big picture state can be put together.
You know, Boltzmann knew he'd stumbled onto something absolutely fundamental about how the universe works. He was the one who finally connected the hidden world of atoms with the everyday world of heat and energy. And this idea was so important to him, so profound, that this exact formula is carved on his gravestone in Vienna. That's his legacy.
Okay, so now that we have Boltzmann's bridge connecting the micro and the macro, we can finally make sense of one of the most famous and maybe one of the most misunderstood laws in all of science.
I'm talking about the second law of thermodynamics. You've probably heard it summed up as everything always gets more disordered, or chaos always increases. But with what we know now, we can see it's not some mysterious cosmic force pushing everything towards a mess. It's just about probability.
Here's how it works, and the logic is actually pretty straightforward. First, any system is constantly, randomly, just shuffling through all of its possible microstates. Second, any one of those microstates is just as likely as any other. But, and this is the big one, some macrostates have way more microstates than others. So what's the result? The system is just statistically guaranteed to end up spending basically all of its time in whatever macrostate has the most ways to exist, the one with the highest entropy.
And boom, that brings us right back to our cup of coffee. Think about it. The macro state where everything is a uniform, lukewarm temperature, with fast and slow molecules all mixed up, has an absolutely astronomical number of possible micro-arrangements. It's way more than the number of arrangements for the hot coffee cold room state, where all the fast molecules are neatly contained in the cup. The coffee doesn't want to cool down. There's no force making it. It just naturally, randomly stumbles into the state that is overwhelmingly, massively more probable.
This quote really just nails it. Equilibrium isn't some special, magical state that things are forced into. It's just the state that has the most possible ways of existing. It's the champion of probability. The system isn't being pushed anywhere. It's just wandering around and ending up in the biggest room in the house.
And that leaves us with one last, kind of mind-bending idea to chew on. You know how we feel time? How it only moves forward, like a one-way street from the past to the future? Well, what if that arrow of time is nothing more than the entire universe doing exactly what our little cup of coffee does? Just simply and inevitably moving from states that are less likely to states that are overwhelmingly more likely. Just something to think about.